So far in this video series, we have found that all of the infinities we've looked at are the same. We've shown that the cardinality of the natural numbers is the same as the cardinality of the integers, and that the cardinality of the integers is the same, the cardinality of the naturals is the same as the cardinality of the rationals. This does in fact mean that the cardinality of the integers and the cardinality of the rationals is also the same. I won't go into much detail about that for now, but you may be starting to wonder if this is a very useful path to go down, if maybe there really is only one kind of infinity, and all of these different sets that have infinite elements are really the same, and they have the same cardinality for all of them. But we can't assume that, so we can continue to look at new sets, and in this video we're going to be comparing the cardinality of the naturals with the cardinality of the real numbers. So the naturals, again, are just 1, 2, 3, counting on forever. The reals, I haven't written out the set in any explicit notation because I'm not really sure how to. It's any number, it's basically any number. It can be a rational number or an irrational number. And I think it makes more sense to talk about the reals in terms of what they are not, so that you don't just think that they are absolutely everything. So we can talk about imaginary numbers. So there's no real number equal to the square root of -1. So in math, we've introduced this concept of imaginary numbers. Well, I shouldn't say we. Mathematicians in the past have introduced this concept of an imaginary unit, I, which is equal to the square root of -1. And then there's the complex numbers, which are of the form a plus bi, where a and b are real numbers, but there's a real component and an imaginary component. So these are not in the reals. And then we can also talk about vectors. If you've taken any multivariable calculus or linear algebra, you'll be familiar with sets like R2, R3, or in general Rn. So R2, an element of R2 might be written like this. So you can have it has two components, and you can think of this as an x component and a y component, where it's a vector which has magnitude and direction, and a would be the x component right here. This is a, and b is the y component. So that's one way of thinking about it. R3 is vectors with three components, which has a length, a width, and a depth. And then you can expand this idea to any number of dimensions. It's not possible to visualize, as far as I know, anything higher than 3 dimensions in the space that we are familiar with, but mathematically it is very possible to work with higher dimensions. So this is just to give you an idea of things that are not real numbers, but basically any number that's not a vector and not imaginary or complex is going to be real. This includes all the rationals and irrationals. So now let's try and compare the cardinality of the naturals with the cardinality of the reals. And recall, again, we can look at the intuition here on a number line, where we have just some natural numbers, which can include 1, 2, 3, and so on, evenly spaced forever. But this entire line is just real numbers, where anywhere you put your line is going to mark a real number, no matter what. Even if it's over here at pi, even that is a real number. It can't be expressed as a fraction, where the numerator and denominator are integers, so it's not rational, but it is real. Anything on this number line is going to be a real number. And again, it seems like there are just a lot more real numbers. All of the naturals are real numbers, and a whole lot of other things are also real numbers. So our intuition would say that there are more reals than naturals, but the same intuition is there for the integers and the rationals, and in both cases the cardinality turned out to be the same. So the question we have to ask ourselves is, does there exist a bijective function from the naturals to the reals? And again, bijective means that every natural maps to a different real number, and the naturals, there's one natural mapped to every real number. So now try and think about this a little bit on your own, and I will present the solution in a few seconds. So let's think about what it would mean for there to be a function that maps every element, a bijective function from the naturals to the reals. it should mean that we can construct a table where on the right side we have natural numbers, and on the left side we have natural numbers, and on the right side we have real numbers. So we can list the naturals straightforwardly, 1, 2, 3, and continuing. It's hard to tell how we might want to list the reals. A decent starting point might be 0, but then where do you go next? You could try 0.1, but you can go smaller than that. You can do 0.01, or you can do 0.001, and you can have as many zeros before that 1 as you would like. So there's no clear next number. So maybe it seems kind of difficult to arrange the reals systematically, but that doesn't mean that we can give up just like that. And this might kind of give you an intuition that this is even different from the integers and the rationals, where we could come up with a way to systematically arrange them. But maybe there's some creative way to do it that we just haven't thought of right away from the simplest possible technique, which is just looking for an immediate number that comes right after 0. Maybe there's some other way to do this. And if we want to show that there is a bijective function, we need to find that way to arrange the reals. But as it turns out, and I'm giving you the answer here, there is actually no such bijective function. There's actually a larger cardinality of the reals than of the naturals. And now you may ask how it's possible to know that, how you can prove that there's no bijective function. And this was actually proven by Georg Cantor, and it's a famous diagonalization argument. And essentially, we are trying to find a way to arrange the reals such that every one will be in this table somewhere, and the corresponding natural will be what the function takes as an input to then get this real number as an output. So now we're just going to suppose that there is some way to do this, some way to arrange the reals so that eventually you get to all of them in this table, and that way every real will have an associated natural somewhere on this table. And this has to be possible if there is a bijective function from the naturals to the reals, because it would be possible to arrange them in a table like this, with f of 1 being the first entry in this column, f of 2 being the second entry in this column, and so on. But we can show that this is actually not possible. And so the way we can do this is take any arrangement of the real numbers in this column. And I'll write a few random real numbers here, 1, 4, 1, 5, and let's use, so this is like an infinite decimal. Let's say this is a irrational number, but then we can also have just 1, but let's write that as 1.0000 and so on. It'll have only zeros the whole time. It's just the regular number 1, but we'll just write it this way because it'll, and you'll see why in a moment. Then we can have maybe pi, which is close to that. I see that I wrote it like that. But yeah, let's add a couple more here. Let's have 5.5, and then again just zeros would follow, and so that should be enough. So now we're also going to suppose, remember this is still an infinite column even though I've only entered 4 values, and the way we can show that there is no way to arrange the reals such that this table maps natural to every real is by showing that no arrangement allows, for any arrangement, you're guaranteed to be missing at least one real number, and one real number is nowhere on this list and has not been mapped onto by a natural yet. So how can we show this? The goal is to find a number which is different from all of these numbers in the column, and another way of saying that it's different from all of these numbers is that at least one decimal place is different, and it could be a place that's before the decimal point, but at least one digit is different somewhere in the number. And you can create a number which is not on this list and which differs in at least one decimal place in the following manner. You can make sure that it disagrees with the first digit of the first number. So let's write our new number down here. So the number right before the decimal in this case is 0, so let's just pick 1 as the first digit. So now whatever we have after this, clearly this new number is not the same as the first number because it has a different number in this, a different digit in this place. Then we can make sure that it also differs from the second number by making it differ from the second decimal place here. And so this is a 0, we can make that also into a 1. And so clearly this is also different from the second number because it has a different different digit right after the decimal place. Then you can continue going downwards and across. So 4, we can turn that into a 5. Another 0, we can turn that into another 5, into another 1. So you can see that we are guaranteed, no matter what the other digits in this new number are, it's guaranteed to be different from these 4 numbers because it disagrees with the place before the decimal with the first number, the first place after the decimal with the second number, the hundredths place with the third number, the thousandths place with the fourth number, and there are infinite entries in this list. We're imagining that it was possible to arrange all of the reals, and so there's an infinite number, but all of them can be written as infinite decimals, including the ones which aren't actually irrational or repeating, such as 1, but you'll just treat that as a long list of zeros. And so by continuing to make sure that all of these digits disagree with the corresponding digit of on this diagonal, you are creating a number which is not the same as any number in the list you've already created. For this reason, it is clear that there's no way to list the real numbers that matches them one-to-one with the naturals. And this demonstrates that for the first time we have shown that there's a set, the real numbers, such that its cardinality is larger than the cardinality of the naturals. And what does it mean to have a cardinality larger than an infinite cardinality? Because there are infinite natural numbers, and there are names given to each of these cardinalities. The cardinality of the naturals is said to be aleph null, which is also known as aleph naught. I'm not very good at writing this symbol. You can actually watch a very good video from Vsauce, which honestly, if you're watching my videos, you've probably already seen, called How to Count Past Infinity to see the symbol written better and also to get some other intuitions about infinities, which is, a very, very interesting video. So this is aleph null, and the cardinality of the reals is also called the cardinality of the continuum, written something like this. This is also sometimes written as 2 to the power of aleph null. And this is an interesting thing to see. There's no reason to think that this should be 2 to the power of aleph null, given what I've told you so far. But in an upcoming video, I will show you why it is written like that sometimes. But just to recap, we have now found that using this diagonalization argument, we can see that it is always possible to construct a new number which is not on this list, and therefore there's no bijective function from the naturals to the reals. And therefore, the cardinality of the reals is actually larger than the cardinality of the naturals, and we have to deal with a truly larger type of infinity that we have not seen yet. Thanks for watching.